Everyone, my name is Martijn, and today I will be talking about our work. Making more of little data. Improving low resource automatic speech recognition using data augmentation. For many low resource languages, such as minority languages, regional languages, or dialects, automatic speech recognition performance remains much lower compared to high resource languages such as English. In this work, we're going to investigate whether data augmentation through self-training or the use of a text-to-speech system could help improve low-resource ASR performance. While prior research emphasizes the benefits of data augmentation techniques to improve automatic speech recognition performance, limited conclusions can be drawn from these works in a very low-resource, real-world setup we consider in this work. The languages we consider are shown on this slide. We use 4 hours of manually transcribed speech data from Gronings and West-Frisian, which are spoken in the Netherlands, and Nasal and Besemah, which are spoken on Sumatra. For Gronings, we perform additional data augmentation experiments. And for this language variant, we have additional training data available. For our experiments, we use the pre-trained ACL model with 317 million parameters. This is a multilingual model that is pre-trained on 436,000 hours of speech in 128 different languages, which are primarily Indo-European languages. The architecture is similar to Wave2Vec 2.0 and consists of a convolutional encoder, a quantizer, and a 24-layer transformer model. We also investigate whether it's beneficial to further pre-train the ACL model using limited data and computational hardware before we fine-tune the model for automatic speech recognition. As pre-training is computationally expensive, we only evaluate this for Gronings. We fine-tune ACL on various amounts of training data from the 4 languages. The 4 hours we have available, we divide it up into 80% for training and 10% for both development and test data. So we start with a full data set of 192 minutes, which is 80% of 4 hours. And then we create smaller subsets down to roughly 20 minutes. On this slide, we show our self-training approach. So we use the subsets to fine-tune an ACL teacher model. This teacher model then transcribes the remaining speech data from the full training dataset. The combined data, which is the manually transcribed and the automatically transcribed speech, is then used to fine-tune a student model. This student model ideally outperforms the teacher model. In our broader set of experiments on Gronings, we performed 3 self-training iterations. Initially, an ACL teacher model was fine-tuned on 24 minutes of data and used to transcribe 168 minutes of unlabeled speech. Next, student models in the second and third iterations transcribed an additional 168 and 336 minutes. After each transcription phase, a new student model was fine-tuned. For our TTS experiments, we use an existing TTS system, as not all very low resource languages have sufficient amounts of data available for developing such a system. And using this system, we generate synthetic training data using the transcripts of the same sets of recordings that were used for the self-training experiments. We see that the performance increases as the amount of manually transcribed speech increases. However, self-training also clearly shows benefits across all languages, and the student models outperform their teacher models in almost all cases. On this slide, we show the results for continued pre-training on Gronings. We see that this resulted in very small performance gains. Roughly up to 9% performance improvement was observed when fine-tuning with only manually transcribed speech data, and the performance gains were really minimal when self-training data was used. Now we show the effects of using additional augmented training data. Our results for self-training show that increasing the amount of automatically generated fine-tuning data is beneficial, although to a lesser extent than the benefit of using the first set of 168 minutes of speech with automatically generated transcriptions. We also show that an even larger performance gain can be achieved when using an existing TTS system to generate additional training data. Generating a larger set of synthetic speech had no clear advantage. The top performing TTS augmented model performs similarly to the model trained on 96 minutes of manually transcribed speech data. These results might, however, overestimate the model performance, as the speaker whose data was used for training the available TTS system was also included in the Gronings test set. On the right, we report the performance on the out-of-domain test set. And while the performance is worse compared to the original test set, the patterns of the results for the self-training approach remain similar. Also, the benefits of augmenting the training data using a TTS system is still present. So to conclude, data augmentation can effectively improve low-resource ASR performance. And the greatest performance gains were observed when increasing the amounts of manually transcribed data. But self-training and TTS system augmentation also showed substantial increases in model performance. Thank you all very much for listening, and feel free to reach out for more information or if you have any questions.